Hello everyone, my name is Leo Stone, my partner is Rishi Ranjan, and this is our presentation, Bug Hunting with WinFuzz. So I'll just start off with a little bit of background about fuzzing for those of you that don't know. So fuzzing is an automated software testing technique, and the goal of fuzzing is to find bugs in software. And fuzzing works by generating randomized inputs, which are called test cases, for the program that you're testing, and then passing it to that program, which is called the system under test here. And when you pass those randomized inputs to the system under test, you observe its behavior to see if you can detect any incorrect behavior while it's parsing that input. So typically this would just mean you check to see whether or not the program crashed while parsing that input. Because if it did crash, that means you've probably found a bug in the system under test. And fuzzing has been very effective generally at finding bugs in all kinds of software. There are fuzzers for operating system kernels, for network software, user space software, of course, basically any kind of software that accepts input. And sort of the most obvious naive way of doing fuzzing would be to just generate a stream of completely random bytes and then feed that to the program you're testing. But modern fuzzers have to be a little more intelligent to get good results. So they will typically do something that's called feedback-driven fuzzing, which works like this. So we start with a group of seed inputs, which is just a group of valid inputs for the program you're testing. So if we're writing a program that parses PNG files, the group of seed inputs is just a group of valid PNG files. This group of seed inputs might contain like some potentially interesting edge cases, like maybe one of them is just 1x1 pixel, maybe one of them has a weird odd resolution, maybe one of them is in grayscale or something like that. But they're all valid PNG files. And then those get fed into what's called the input queue, which is used for test case generation. So the fuzzer will take inputs out of this queue and then do test case generation, which means modifying that input slightly in order to hopefully cause some new interesting behavior in the program. So the fuzzer takes inputs from the queue, modifies them slightly in this step, and then that produces a test case. So then the fuzzer runs the target binary and passes that test case to it and monitors the target program as it's parsing that test case. So then we use instrumentation typically to detect which regions of the code in the target binary that test case is reaching, so that we can tell when a test case reaches a new, previously undiscovered region of the target binary. And if that happens, then that test case is called a coverage increasing test case, and we can feed it back into this input queue. That's where the feedback driven part comes from, because we're trying to sort of look for inputs that cover new regions so we can gradually try to cover the whole program, hopefully. And then if something really interesting happens, like if the system under test crashes outright, then we save that test case that caused the crash into a separate list so that a human can look at it later, debug the target program, and hopefully try to find and fix the underlying bug. So now I'll just get into the setup of our fuzzing experiment. So we chose to use WinFuzz, which is a new Windows fuzzer that we actually developed. And it was sort of created to address this gap between Linux and Windows fuzzing. So a lot of you probably already know about the fork system call, which is a system call that will efficiently create a new process from the one that calls fork. And this is very convenient for fuzzing because you want to run the same program over and over again. So you can use fork to create new copies of this program very efficiently. But of course on Windows, there is no fork. And so Linux fuzzers that use fork are generally a lot more effective than fuzzers on Windows because they don't have access to a really good mechanism for cloning processes efficiently. So WinFuzz basically aims to address this gap with a new technique for executing the target. So there's an existing Windows fuzzer called WinAFL, which uses what's called persistent mode. So the idea behind that is, what if instead of creating a new process every time we wanted to run the target, we just jumped back to the beginning of the target? So this way we can actually avoid the process creation and teardown code. So that's nice because we get to take off a lot of overhead. But the problem is, if during program execution we change any of the program state, like global variables or anything like that, those changes will persist because we're not tearing down and creating the process anymore. We're not reinitializing those global variables. So those changes persist across runs, which translates to persistent mode being incorrect. So WinFuzz basically builds on top of persistent mode because persistent mode is very efficient, but it's incorrect. So we want to take that efficiency, so we build on top of persistent mode, but we want to fix this correctness problem that it has. And we do that by adding our own code to take a snapshot of the program state and restore it every time we want to run the program. So now we still jump back to the beginning every time the program finishes an iteration, except this time we don't just start running the program again immediately. We jump back, then we restore program state from the snapshot, then we run the program. So that's just a high-level overview of how this fuzzer works. And so for choosing the program that we actually wanted to fuzz, we basically wanted to look for some popular or like relevant to someone Windows compatible software that isn't already on OSS Fuzz, which is Google's fuzzing framework, because OSS Fuzz just has orders of magnitude more computational power than we have access to, so we can't really compete with them. But we found a header-only C++ library that parses WAV files called AudioFile, which was a good candidate. So I created a simple harness program for that just uses AudioFile to load a .wav file from the command line and then print some basic information about it. And so we ran 7 fuzzing trials using this harness for 48 hours each, and one of them found a crashing input. So that brings us to the actual bug. So in order to understand the bug, we have to first talk a little bit about the actual file format. So the WAV file format is used to store audio data, but it also needs to store like other metadata, like metadata for the audio, metadata for the whole file, potentially other types of metadata. But each type of data is broken into a separate chunk, and each chunk has its own header. That's basically all you need to understand here. So you can see here, this is the beginning of the file, and then everything after that is just basically a sequence of these chunks, and each chunk has an ID and then a size and then the rest of the data for the chunk. That's all you have to really understand to understand this bug. So the audio file library needs to parse each chunk to interpret the file. And to do that, it uses this helper function called getIndexOfChunk. So this is just trying to go through the file and find the byte offset of a given chunk. So if you're looking for data, this function's supposed to give you this offset here. And it does this by iterating through all of the chunks to find the chunk that has this ID that you give it. So the problem is that audiophile will actually parse a value directly from the file and then add it to the loop counter here. So here, this is the end of a for loop here. And it parses this 4-byte signed integer value from the current offset in the file. And this is supposed to be this chunk size. So when it parses this chunk size, it gets that value and then adds 2 times data length, which is 8, plus that value it parsed to the loop counter. The fuzzer generated an input where chunk size is -8. And so, of course, then that means it's adding 0 to the loop counter, which puts the program into an infinite loop. And if you wanted to, you could use this bug to do a denial of service attack against a server that was using this library in its backend. So if, for example, you had like some web service that hosts user-generated audio content or something, and they need to like parse a WAV file to convert it to a lossy format or something like that, like SoundCloud or Bandcamp, an attacker could upload a WAV file with a -8 chunk size and then tie up a little bit of the server's resources stuck in that infinite loop. So now I'll demonstrate that attack. So I'll just use netcat as a stand-in basically for the web server and web client here, but the idea is still the same. So over here on this left terminal, we have the netcat representing the server. So if we just listen on this port for input and then pass the input to the audiophile program that we're listening, and then we connect the client. So imagine this is the malicious client, and we're passing it in this input that the fuzzer generated here that causes the infinite loop. And then we connect the client, and nothing happens over in the server. And that's because, as we can see here, it's still going. It's stuck in an infinite loop. It's consuming one CPU completely. So you could imagine if an attacker were to do that enough times, they could tie up a significant amount of the server's resources. So I'll just end with this semi-relevant KCD comic about sanitizing your database inputs. So the security takeaway here is always make sure you validate or sanitize data that you're taking in from an external source. Thank you.